During our last few classes, we discussed the probability distributions. We said the most important probability distribution is the normal distribution. We use the normal distribution to model the continuous random variables whose histogram looks like a nice symmetric bell curve, right? And we talked about some other probability distributions as well for various random variables. We classified random variables into two classes. We said we have continuous random variables and we have discrete random variables. And we have a set of possible probability distributions for continuous random variables, and we have another set of possible probability distributions for discrete random variables. For example, we said for a discrete random variable, we may use the binomial distribution, Bernoulli distribution, depending on the cases, Poisson distribution, discrete distribution, or discrete uniform distribution. And for continuous random variables, we said, other than the normal distribution, we can also use the uniform distribution, chi-square distribution, t distribution, f distribution, and so on, provided those histograms of those random variables confirm that the shape of the distribution is one of those specific shapes. All right, so let's say, for example, I collected a data set on a continuous random variable, weights of the males between 20 years and 30 years of the entire world, or in the entire United States. So the random variable is the weights of those people between 20 years and 30 years, males. There's practically no way that I can collect all the data points. Okay. What I can do is I can take a small sample and see the distribution. I can, of course, draw a histogram, and if it looks like a symmetric bell curve, I can safely assume that the random variable weights of males between 20 years and 30 years of age follows a normal distribution. But on the other hand, if you look at the normal distribution, when you write down the normal distribution using the standard notations, we write it this way. X, whatever the random variable, is distributed normal with mu, comma, sigma squared. Now what are these two? They are called parameters. Remember, we of course used those terms, parameters. And if you look at some other probability distributions, such as, let's say, Poisson distribution, for example, in standard notations, we wrote Poisson distribution as Poisson lambda. And if you look at the t distribution is often written T and subscript whatever the degrees of freedom. And if you look at the chi-squared distribution, you write a chi-squared and sub k, where k stands for the degrees of freedom. And if you look at the f distribution, you write d1 and d2 as the degrees of freedoms. There are 2 degrees of freedom for that. And if you look at the uniform distribution, you write uniform. Some people write just unif, and some people write uniform, and some people just write a u, a to b, where a is the starting point and b is the ending point, and it's a nice rectangular distribution. So a and b are the parameters. Now, the problem of not knowing the parameters is a very serious, challenging problem in statistics. Of course, the reason is we define these distributions for a given random variable. So our random variable could be the same example that I took earlier, such as the weights of the people. And it's not going to be practical to find every single person's weight, because mu, for example, mu of the normal distribution stands for the mean. It's a parameter, and that parameter stands for the mean, and sigma squared stands for the variance. Sigma stands for the standard deviation. And there's no way that I can actually calculate these values unless I have every single data point that corresponds to the random variable. And collecting every single data point for a random variable is actually not practical. Then what? That part is going to be discussed during the next 2 chapters of your textbook. Chapter 8 is sampling and chapter 9 is experiments. As always, I have posted this lecture note on Canvas, so please go ahead and download it, and then you can watch the video and fill the blanks with me. And as usual, that's how we are going to understand the lecture. All right, now if you look at point number 1, I have written down parameters and statistics as the point number 1. All right, so what are the parameters? We already talked about the parameters. Those are the entities required to completely define the distributions. So we'll write it down as that. Parameters are the entities required to completely define the distributions. For example, normal distribution, the parameters are mu and sigma squared, right? And for the Poisson distribution, now you know what are the discrete probability distributions and what are the continuous probability distributions. Normal distribution is a continuous probability distribution. Poisson distribution is a discrete probability distribution. And there's just one parameter, which is the rate, is given as lambda. Okay? And likewise, you can come up with any other probability distribution as well. Uniform distribution, for example. Uniform, I would say, A to B distribution. So the parameters are A and B. Now, they are the examples of the parameters. And we'll write down 2 additional notes. Distributions are defined for a specific random variable. Okay? Distributions are defined for random variables. You know, R dot V dot. That's my abbreviation for the random variables. So distributions are defined for random variables. Often, collecting every single observation for a random variable is not practical. Okay? If I define the random variable as temperature today in Kansas, even at noon, there is a specific time, how many readings I can obtain, that can't even be defined properly. Okay? I can select 100 locations, I can select 1 million locations, and I can keep taking the temperature at noon today. So, availability of every single data point for a given random variable is almost not true. They're not available for analysis. Okay? So I will say distributions are defined for random variables. Every single data point of any random variable is almost always not available. Now that causes a problem. What's the problem? If I don't have every single data point of a random variable, I cannot calculate the values of these parameters. Mu is the mean of every single data point. And I don't have every single data point, and therefore I cannot calculate mu. And the same way I cannot calculate sigma squared. And the same holds true for every other distribution as well. Of course, for the Poisson distribution, I know lambda is also the mean as well as the variance. So I need to calculate the mean in order to find lambda for that distribution. Well, A and B for the uniform distribution, they are the endpoints. A is the starting point, B is the ending point. And I will still need a dataset to properly calculate A and B. Maybe I can calculate mean. Mean is given by A plus B divided by 2 for the uniform distribution, if you remember. Okay? And also I can calculate the variance for the uniform distribution. So the variance is given by B minus A, everything squared, divided by 12 for the uniform distribution. And if I have those 2 equations, maybe I can manipulate and obtain A and B. I can solve the simultaneous equations, 2 simultaneous equations for the mean and the variance. But even for that, to calculate mean and variance, I will once again need every single data point, which is not existing. So we say always or I would say almost always, the distribution parameters are unknown. Okay? So almost always, distribution parameters are unknown. So what? If they are unknown, if I still need the distributions also, because to analyze our data, in the future we'll see that we will need distributions. And that's the whole purpose of statistics, analyzing the data. So what we are going to do is, we are going to estimate the parameters. How do you estimate the parameters? You just take a sample of data points and calculate a sample mean, for example. And you can calculate a sample variance and so on, okay? So, we know the parameters, properly defined. Now we can define the statistics. The statistics are defined as estimated values of the parameters. We've already seen a couple of estimated statistics, estimated values of the parameters or the statistics. For example, x bar. This is the sample mean. It's a statistic. And s squared, which is the sample variance. And s, which is the sample standard deviation. They are all estimated values of the parameters. Therefore, they are called statistics. Okay? All right, so that's what we have to write down under point number 1, parameters and statistics. So we know the difference between the parameters and statistics. Now we will go to point number 2. In point number 2, I'm going to define a population and a sample. So what's a population? Population means the collection of every single data point of the random variable. Okay? That's called the population. So on the point number 2, first part is population. It's a collection of every single data point of the random variable x. That's how you can define it. If it is temperature, every single temperature reading. If it is the weights of males between 20 years and 30 years of age, all such weight readings will be the population, okay, and so on. So it always depends on the random variable, the way you define the random variable. We'll do a few more specific examples in a minute. At this point of time, remember, of the random variable x, that part is very important for the complete definition of the population. We say population is every single data point of the random variable x. So population depends on the way that you define your random variable. Okay? We'll do a few examples in a minute. But before that, we'll also look at the sample. How do you define the sample? The sample is defined as any subset of the population. Any subset of the population. Usually, what we have in hand for calculations or the analysis is always the sample. Okay. So, what's an example? We said we will let X be the weight of males between 20 years and 30 years of age of the United States. If I define my random variable as that, the population will be all the males between 20 years and 30 years of age in the United States. Right? And a possible sample, I'm going to select 30 males of that age group just randomly. So that selected 30 will be the sample. Now I'm going to slightly modify the definition of my random variable. I'm going to let x be the random variable, and that random variable is the weights of the males between 20 years and 30 years of age, but not in the entire United States. But this time I'm going to define it as the males of that age group in Kansas. If I define it that way, my population is all the males between 20 years and 30 years of age in Kansas. Now I can take a sample of 30 Kansans of males who are in that specific age group, and that selected 30 will be my sample. Let's say I'm going to slightly differently modify that random variable. Now here's my new random variable x. The weights of the males between 20 years and 30 years of age from Kansas State University. Now what's my population? All the males of 20 years and 30 years of age from Kansas State University. That's my random variable, and that's my population therefore. Okay? And a sample maybe, I'm going to select just 30 people from Kansas State University, males, satisfying that age group definition. In that case, that will be my sample. Okay? So please specifically pay attention to the definition of the random variable x when you identify the population. Okay? Because every single data point of that random variable is defined as the population. All right, so that's point number 2. And let's go to point number 3. Identify the population and the sample in each of the followings. Part A, to study the grade distribution of college algebra in all the tier 1 universities of the United States, 1,000 students will be selected. So what's the population? All the students in the tier 1 universities of the United States. The sample is the selected 1,000 students. Part B, to study the grade distribution of college algebra in Kansas State University, 100 students will be selected. What's the population and what's the sample? The population is all the students in Kansas State University. The sample is the selected 100 students. Look at the next example. A bank wants to offer a special rate on the credit card holders who charge at least $2,400 a month. On a pilot run, it selected 300 of the customers meeting the criteria. So what's the population, what's the sample? The population is all the credit card holders of the bank who charge at least $2,400 per month. Okay, that's the population. The sample is the selected 300 customers. And part D, to evaluate the specific heat of a copper alloy, 25 specimens are prepared. What's the population? What's the sample? Population is all the copper alloys, right? All the copper alloys on Earth. Sample is the selected 25 specimens. So understanding the population and sample will be extremely important. And for your second exam, you can always expect one question to identify a sample and a population. Okay? All right. Let's move on to the next point. Now we need to slowly start the collection of data. That means we have to see how to select the sample properly, scientifically. Unless you collect your data properly, scientifically, your calculations will not give you any reliable results end of the day. To predict the matters outside of the collected sample, first, the sample should be properly and correctly collected. So how do we do that? Now, scientific method of collecting data for a sample depends on the nature of the population. We are going to discuss 2 scenarios. Those 2 scenarios are given under point number 4. Homogeneous versus heterogeneous populations. There's one specific method to collect data for a sample from a homogeneous population, and there's another specific method to collect a sample from a heterogeneous population. So first we have to see what are the homogeneous and heterogeneous populations. A homogeneous population means with respect to your random variable, every single subject of the population can be considered uniform or homogeneous. Now that part can be more easily understood if I also talk about the heterogeneous populations. In a heterogeneous population, with respect to the random variable, you can identify different groups. Subjects in the population will not be the same. Let's look at an example. Think about, I need to get an opinion survey regarding the fast food consumption of the United States. Now for that objective, I can consider all the people in the United States as homogeneous. And think about a different definition of the random variable. Now I need to do an opinion survey regarding how is the President of the United States perform at this point of time. Now for that purpose, we can assume that the population of the United States is not homogeneous because we have highly red states, we have highly blue states, and we have highly swing states. Now because of that reason, I can identify different groups. So let's define the homogeneous and heterogeneous populations one more time. In a homogeneous population, with respect to the random variable, every single individual or the subject can be considered homogeneous, just similar. Okay? In a heterogeneous population, with respect to the random variable, you can identify different groups. Those groups are called strata. Within each stratum, the subjects can be considered homogeneous, but between strata, the subjects are different. Often, the very natural heterogeneous population is the human population. We have males and females. So we have at least two groups, right? So likewise, whenever, with respect to a certain random variable, if you can figure out different groups, of course, if you look at the strength, physical fitness of the human population, I have to see there are two groups. On the other hand, if you need to see the ability of education, with respect to that random variable, the human population cannot be classified into male and female, right? In that case, there may be no difference between males and females, okay? So likewise, with respect to the objective, we can figure out whether your population is homogeneous or whether it has different groups. If so, it is a heterogeneous population. So that's that point. And point number 5 is also very important. Incorrect ways of data collection. We have to avoid the incorrect ways of data collection. Well, there are two basic things that we should keep in mind. So the first thing to avoid is convenience sampling, something called the convenience sampling. Avoid this. Now, what is convenience sampling? Convenience sampling means you collect the data from the subjects where you have the easiest access. Say, for example, I need to figure out the grade distribution of college algebra for all the students in the United States, Tier 1 universities. Now, instead of collecting a sample from all the Tier 1 universities, okay, just to reasonably represent all the Tier 1 universities, I'm lazy and I will just go ahead and select 30 students from my class, my college algebra class. That's convenience sampling. I collect the data from the subjects where I have the easiest access. We have to avoid. Convenience sampling will always lead to incorrect conclusions. Okay, so that's the first thing. There's another thing that should be avoided. when you select a sample, we cannot do bad hidden games. We cannot select biased sampling. We have to avoid. So for example, I need to calculate the average height of a K-State student. Now if I go ahead and select a sample consisting of the tallest students in the university, it is a biased sample. I shouldn't be doing that. When I select a sample, I should select an unbiased sample. That's the most important guideline in selecting a sample. Now, we are moving to the next part. How do we make sure that we select an unbiased sample? That's what we are going to discuss under chapter 8 under sampling. And we said there are two types of populations, homogeneous populations and heterogeneous populations. So for each of the two population types, we will discuss unique sampling techniques. All right, let's move on to the next point, simple random sampling, abbreviated SRS. This is given under point number 6. Point number 6, simple random sampling. This is abbreviated SRS. And there's another sampling technique which also actually has SR and S as the initials, but we don't abbreviate that one as SRS. Okay? SRS stands only for simple random sampling. All right, let's see what is simple random sampling. We do simple random sampling for homogeneous populations. For homogeneous populations. Only. That means with respect to your random variable x, all the subjects can be considered homogeneous. Okay? For homogeneous populations, how do you select a sample? There's just one guideline for that. We have to make sure that every single subject of the population receives exactly the same probability or chance of being selected into the sample. That's a guideline. So let me write it down. Every single subject of the population should receive exactly the same probability which can also be written as chance of being selected into the sample. So how do we ensure that? Now this is all you have to do. You have to take a list of all the subjects. If your population is a human population, you may have the names, but on the other hand, sometimes the names can also be confidential. And in that case, you can have a reference number. Okay? And think about some materials. Let's say I need to find the average tensile strength of aluminum. Well, now I have a huge population. Aluminum for entire world. No, that's not how it's going to work. Analysis is done for a specific population, manageable population. Let's say I'm going to define my random variable as the average tensile strength of aluminum produced in a given factory. It may be within a certain time frame, within a week or within a single day, for example. Okay? So in that case, my population will be all the aluminum produced in that factory. So I can label them. Every single thing can be labeled, okay? Every single subject can be labeled. So that's what you have to do first. You have to take a list of the entire population, list of names or list of reference numbers, something like that. I need a list of subjects of that entire population, entire homogeneous population. And then, to ensure the same probability, I'm going to do something. So we can do it in MS Excel quite nicely. So the first column of MS Excel is for the list. And in the next column, I'm going to use a probability distribution. Now, can you suggest me a probability distribution which assigns exactly the same probability for every single subject? So we've seen so many probability distributions, right? So tell me one probability distribution which can be considered as assigning exactly the same probability for all the values of the random variable. It is the uniform distribution, uniform A to B distribution. So in a uniform distribution, you can have a starting point and you can have an ending point. Between those 2 points, for all the values of the random variable, we have exactly the same probability being assigned, okay? So, to select a simple random sample from a homogeneous population, of course, we use the uniform distribution. We can use uniform any distribution. You can use like 0 to 1 distribution, or you can use uniform 1 to 5 distribution. You can use uniform 10 to 50 distribution. The parameters actually are not very important, starting and ending. What's important is that it assigns exactly the same probability for all the possible values of the random variable between those 2 given values, okay? So for the simplicity, let's use uniform 0-1 distribution. We can use MS Excel and generate random numbers from this distribution quite easily. So I will label the second column as random numbers. I'm going to define random numbers. I'm going to generate random numbers from the uniform 0-1 distribution. 0 and 1, that's not required. You can pick any of these values. And let's say I had 100,000 subjects in my population. Then I must generate 100,000 random numbers. Okay, so each subject in this list will now have a certain random number assigned. What we do next is, we are going to sort this data set. Now we have to remember one thing. When I say random numbers, they are random. There's no specific order of the numbers in this column, in the second column. The second number could be larger than the first number, and the third number could be smaller than the second number, and so on. They're not in any specific order. So what we are going to do next is, we are going to sort the data set. Okay? We are going to sort the data set according to the ascending order of the random number. Okay? We select the random number. We are going to sort the entire data set according to the random number, so that after you sort the data set, the second column will be listed from the smallest random number to the largest random number. And accordingly, the list of names will also be adjusted, because I sort the entire data set, and then all I have to do is to select the first n as a sample. So if n is equal to 100, n is a sample size, select the first 100. Okay? So that's how we can select a simple random sample. All right, I will show you the steps of selecting a simple random sample using MS Excel. Let's go to MS Excel. Here's my MS Excel file, and I have a list of names. Let's say I have 5,000 specimens, and I'm going to label each specimen with a number from 1 to 5,000. So if you scroll down, you can see that the list goes until 5,000. Each specimen in the population has received
a certain reference number. So the next thing I have to do is I have to generate random numbers using the uniform distribution. I will have to generate 5,000 random numbers. In order to do that, I have to go to data and select data analysis toolpack. So if you're using MS Excel for the first time, the data analysis toolpack will not be available to you by default. You have to separately import it. And I think I have shown it to you earlier how to import the data analysis toolpack. But in this video also, I will real quickly show you once again how to import the data analysis toolpack since we're going to use it. You have to first go to File and select Options and select Add-ins. Select Analysis Toolpack, then Manage Excel Add-ins, click on Go, and then you have to check this box, Analysis Toolpack, and then click on OK. Now, if you go to Data, you will see the Data Analysis Toolpack. Click Data Analysis Toolpack, and then you can scroll down, you will see the function Random Number Generation. Select that function, click on OK. I just need one variable as random numbers. I will need 5,000 data points, of course, but number of variables is 1, so I will enter 1 in this field. Number of random numbers I need is 5,000 because I have 5,000 labels in the list, and then I have to select the distribution. We said the distribution should be uniform. Select uniform, and then you have to define the parameters A and B. So the default values given by MS Excel for the uniform distribution are 0 and 1. We will just leave them as that. And if you need to generate the same set of random numbers again, then you have to specify a random seed. I, of course, don't want that because I just need to generate random numbers one time. So I will just leave that field blank. The output range, I will check this little circle, click on this little arrow, and select the first cell under the label random numbers. And then you can move your cursor back to this little arrow and click that, or you can simply hit enter. That's basically all you will need. And then I will click on OK. Now I have generated 5,000 random numbers. As you can see, the generated random numbers are not in any specific order. What I have to do next is to sort the entire data set. Before doing that, I have to first select the entire data set, which I will do by selecting the very first column label, and then I will press Shift. With that, I will click the right arrow key. And after that, I need to select the entire data set. So I can press Shift and hold and keep pressing the down arrow key, but it's going to take forever. So we are going to use a shortcut. The shortcut is Shift, Control, and down arrow key. All three keys are pressed at once. Now the entire dataset is selected. So what I have to do next is to sort. Once again, you have to go to Data and select Sort. And then you can define Sort by. Click that little arrow and select Random Numbers. Sort on cell values. I would like to sort them from the smallest to the largest value of the random numbers. And that's basically all. And click on OK. Now you can see that the list is also changed. So if I need a sample of 20, I have to just select the first 20 numbers appeared in that first column under list. So that's how you should select a simple random sample using technology.
All right, let's move on to the next point. Point number 7. A quality control engineer wants to test the mean tensile strength of aluminum. The dimensions are given. Those rods made in her factory. Explain how to select a sample of 12 rods for testing. It's very important. You can expect one question like that for your exam number 2. Okay? So we will have to explain all these steps. So I will take all the rods made in her factory. That's the population. And I'm going to label them from, let's say, 1 to whatever the last number. If she had 10,000 aluminum rods produced in her factory, I had labeled every single aluminum rod from 1 to 10,000. Okay? And now she wants a sample of 12 for testing. How can we do that? We're going to generate random numbers, sort the entire data set according to the increasing order of the random number, and then select the first 12. That's the sample. Now, the same thing can be done using various other ways. In the past, if you look at a very elementary statistics text, you can see that you can write down the names and put it in a closed box and mix it, and without looking at inside, select 12. That's also one way to do it. But this is 21st century, and we don't like to do it using that kind of primitive methods. Okay, that's the reason we use technology and the proper definition of the distributions and select the uniform distribution for that purpose. All right, that's that. And then if you read part B, even though a sample of 12 rods was selected, only 9 rods were tested for tensile strength. What's the actual sample size n that should be used for any calculations? Well, 12 was the initially targeted size for the sample. That is always not fixed. You have to go back to the data set and see how many data points you actually collected. So in this scenario, she planned collecting 12 readings, but ended up collecting only 9 readings. So the sample is what you have in hand. So for this example, sample size is equal to 9. All right, so that's question number 7. Let's move on to point number 8. Under point number 8, we are going to see how to select a sample from a heterogeneous population. All right, so under point number 8, we have stratified random sampling. Now, like I said earlier, stratified random sampling also has the same initials, SR and S, but we don't abbreviate it as SRS. If you ever see SRS, it only stands for simple random sampling in all statistical literature. Now, stratified random sampling. Stratified random sampling is used to take a sample from a heterogeneous population. So that's the first thing I will write it here for heterogeneous populations. Now, in a heterogeneous population, let's say this is my population, entire population, you can identify subgroups so that within each subgroup, the subjects are similar or homogeneous. But between subgroups, the subjects are different. That's why we call it the stratified random sampling for heterogeneous populations. Okay? So we have subgroups. Now these subgroups are called strata. So this is stratum 1, this is stratum 2, this is stratum 3, and a population can have some number of strata. Okay? According to this diagram, I have 4 strata. So this is my stratum 1. This is my stratum 2, and so on. Now, the population size is given by what letter? What is simple n? Simple n is not for the population size. It is for the sample size, simple n. For the population size, we use uppercase n. This is population size. For the sample size, we use the lowercase n. Now, the entire population has uppercase n number of subjects. And I have several strata. Let's say in first stratum, I have n1 number of subjects, n sub 1. In the second stratum, I will assume that I have n sub 2 number of subjects. In the third stratum, I will assume that I have n sub 3 number of subjects. And here I have just 4, so I will assume that it has n sub 4. Okay. So what's the connection between all these n1, n2, n3, n4, and n? N should be equal to the summation of all these numbers, right? So that's very straightforward. So that's the first thing you have to know. N equals uppercase n1, uppercase n2, uppercase n3, and so on. All right, now what I have to determine is how do I obtain the sample of size n. Remember, this n is only an initial starting point. Okay, we use this n, but often after calculations, you get a slightly larger value than the initially assigned n. Let's say lowercase n1 is the number of subjects that I should include for the sample from stratum 1. Let's say n sub 2 lowercase is the number of subjects that should be included for the sample from stratum 2. N sub 3 is the number of subjects that I should include from the third stratum for the sample. And likewise, n sub 4 is the number of subjects that I should include from stratum 4 for my sample. So how do I figure out the values of n1, n2, n3, and n4? Well, I have to make sure that these numbers are proportional to the strata sizes. That makes sense. If a specific stratum has a really large number of subjects, I must give that stratum a priority. I must select more subjects from that stratum. Okay? So, how do you determine the proportions? We determine the overall proportion of each stratum with respect to this capital N. So the proportion for the first stratum will be uppercase N1 divided by uppercase N. And then that can be multiplied by the final sample size that we need, which is N. That should give you N sub 1. Okay? And similarly, you can find N sub 2. N sub 2 will be equal to uppercase N2 divided by N times lowercase n. Similarly, you can find N sub 3. N sub 3 is capital N3 divided by capital N times initially designed sample size, which is N. Likewise, we can continue to do that for all the strata that we have. Okay? And what's the connection between N1, N2, N3, and so on, and the lowercase n? Under ideal situations, the summation of N1, N2, N3, N4, the lower cases, they should be equal to this sample size. But when we do sample size calculations, you can see that this is a ratio, and you're going to multiply it with some number. Often, these calculations will give you decimals as the answers. Whenever you have a decimal, always round it up. We round up because always larger samples provide better estimates. So, let's say for example, you have this calculation. Let's say that gives you n sub 1 equals 21.7. Now this is very straightforward, I have to go for 22. Let's say for the calculation of n sub 2, I got 24.1. Here also, I will not round it as 24. I should round it always up. Okay? So I should take n2 equals 25. Now, because of that reason, we have this connection. N sub 1, lower cases, right? Plus lowercase n sub 2 plus lowercase n sub 3, all these things. The summation is usually larger than or equal to initial sample size, which is n. Okay, so that's that connection. All right, so once you determine how many subjects should be selected from each stratum, the rest is very straightforward. We said within each stratum, the subjects are homogeneous. Therefore, follow the steps of simple random sampling within each stratum. That means to select lowercase n1 number of subjects from stratum 1, select it as a simple random sample for that stratum. Okay? And do the same for the second, third, and fourth. And that's it. That's stratified random sampling. All right, let's move on to question number 9. See if you can identify this as a heterogeneous population, and see if you can answer the given question. So here's the question. A factory plans to buy 400 copper wires from manufacturer 1, 300 copper wires from manufacturer 2, and 200 copper wires from manufacturer 3. You need to estimate the mean electrical conductivity of copper wires using a sample of 20. Explain how would you select the sample. Now we have 3 suppliers, clearly. That means there are 3 strata. And we have to select a sample proportionally to each stratum. Okay? So let's do the calculation. All right, so I will draw a figure like that. That's my population. And so stratum 1 has n sub 1 equals 400. 400 wires are supplied by manufacturer 1 and 300 wires are supplied by manufacturer 2. So n sub 2 should be equal to 300. And 200 wires are supplied by manufacturer 3. So n sub 3 equals 200. And I need a sample of 20. So lowercase n equals 20. So I need to simply figure out how many should be selected from the first one, which is n sub 1, n sub 2, n sub 3. And these should be selected. Okay. So the calculation is very straightforward. What's my capital N? Capital N is the population size. That should be equal to the summation of all these. So 400 plus 300 plus 200, which is 900. Now we can easily find lowercase n1. So n1 will be equal to capital N1 is 400 divided by capital N is 900. That times initial targeted sample size, which is 20. Okay. So if you do this calculation, we get 8.88 something, so 8.89 approximately, and that's very straightforward. So the sample size should be 9, okay? I can round it up. And then I need to determine N2. So N2 will be 300 divided by the total, which is 900, that times 20. So it will be 20 divided by 3, which is 6.67. So this will be rounded, and that will be 7. I will need 7 subjects selected from supplier 2. And from supplier 3, n sub 3 will be equal to 200 divided by the total is 900, that times 20. So that will be equal to 4.44, so on. So that should be rounded as 5. Okay. So if I go ahead and add these values, sample sizes, 9 plus 7 plus 5 is 21, which is actually larger than the initially targeted sample size. But we go for 21 because always larger samples are more reliable for statistical calculations. Okay. The reason we have an initial starting point is because we cannot just blindly allow a large sample. So based on various reasonable estimates, we try to allocate a specific number as the initial sample size. So how do I know I need just 20 to meet all the criteria? So when I have something 20 or slightly larger than 20 can be accommodated, I meet all the required criteria. To know how it happens, we will need some more materials, which you will see in the future. You will need something called the confidence interval and the central limit theorem. So using those, we will see how to figure out the minimum sample size required to reach a certain level of accuracy. That part cannot be discussed at this point. At this point, you will be given the value of the sample size which is initially planned. What you have to do is to determine these strata sizes, how many subjects should be selected from each stratum, okay? All right, so that's it about that stratified random sampling. So once these numbers are determined, you have to select simple random samples from each of these strata, okay? All right, that's it. And that's all about the sampling techniques, and we finished chapter 8 now, okay? Now we can move on to chapter 9. Chapter 9 is about experiments. You will see something called the single factor experiments, and I will also look at an example for two-factor experiments, but in your class, we will not analyze more than single factor experiments. But it's always easy to understand what we mean by a single factor experiment if you also look at multi-factor experiments. We will not see all the multi-factor experiments, but we'll just also see two-factor experiments, okay? Now, this is another way of collecting data. In the previous chapter, we discussed the sampling. If we revisit sampling, what we do in sampling is you just go and observe the values of your random variable. For example, if I need to find the temperature on Earth, I just have one option. I just have to go out and observe the temperature. So it may be a simple random sample for a certain geographical region. Because I cannot heat Earth and find the temperature. Okay? I cannot perturb the subjects of the population in certain conditions. In such situations, we only have sampling techniques, such as simple random sample or stratified random sample. But there are some other occasions where we can do some manipulations, modifications to the subjects of the population, and then find the value of the response variable. So for example, let's say I have to evaluate the efficacy of 2 vaccines for a certain sickness. I can select 2 groups of patients and administer one vaccine to one group, the other vaccine to the other group, and see how they recover, right? And then compare those times. That's a carefully arranged experiment. I decided how many people should be selected for the first vaccine type and how many people should be selected for the second vaccine type, and I injected those vaccines and so on, right? So in that case, I have arranged an experiment carefully. So that's the basic idea of experiments. All right, let's move on to point number 10, single factor experiments. Now, in a single factor experiment, there is only one factor that we allow as something that affects the response variable. We said we are going to measure a response variable. For example, if you administer 2 vaccines to 2 groups of people, you will find the time to completely recover. So time to recover could be the response variable. Okay? So only one factor affects the response variable in a single factor scenario. Okay? So single factor experiments have that special characteristic, I would say. Only one factor affects the values of the response variable. Then what about the other factors? Say for example, I need to find the surface roughness of machined surfaces using end milling. End milling is a nice engineering operation used to machine the surfaces. Now, let's say I need to figure out how spindle speed affects the surface roughness. In that situation, it's a single factor experiment. I can design, let's say, 4 or 5 spindle speeds, maybe 100 RPM, 150, 200, 250, and 300. and I'm going to measure the surface roughness. How about the other things, such as the temperature? As you do the milling operation, the temperature increases in the workpiece. Can I allow temperature to affect the surface roughness? Well, if I'm going to arrange it as a single factor experiment, I should not allow any other factor to affect the response variable. That means temperature should not affect the response variable. So in that case, I will have to use coolant and make sure that temperature is maintained exactly at the same rate throughout the entire experiment. And there are some other situations also occur. Let's say I would like to have 50 machined surfaces. So I need to machine 50 workpieces at those specified spindle speeds. That's plenty of work. What if two people do that experiment? Half of the specimens were machined by one person and the other half is machined by another person. Well, what if one person was a really experienced mechanic and the other person is a new trainee? In that case, their skill level also can affect the response variable. So I have to make sure that all the other surrounding conditions that could potentially affect the response variable, they're all eliminated. Okay, that's the second important condition. Only one factor affects the response variable. Okay, all the other factors, all the other possible causes that might affect the response variable should be eliminated. That's why we say they are carefully arranged experiments. We arrange carefully so that all the other factors that are not considered as official factors affecting the response variable, well, that's why they are called carefully arranged experiments, because we have to avoid any other causes that might unintentionally affect your response variable. All right. So here's an example. The mean tensile strength of synthetic fiber should be found for 4 different cotton percentages: 5%, 10%, 15%, and 20% used in fiber. Okay? The response variable. So the response variable is the tensile strength. That's what we are going to measure end of the day. Factor. There's just one factor. That's the cotton percentage of fiber. There are 4 levels, but it is just one factor, just the cotton percentage. Okay? Cotton percentage is the only one factor. The levels of the factor. It has 4 levels. 1, 2, 3, 4. The first level is 5%. The second level is 10%. The third level is 15%. The fourth level is 20%. Okay? Now, this has just a single factor. When you have just a single factor, the levels of that factor are also called treatments. So, the treatments are also same. Cotton percentage equals 5% is one treatment. Cotton percentage equals 10% is another treatment. Cotton percentage equals 15% is another treatment. And the fourth treatment is cotton percentage equals 20%. Well, that kind of experiments we will analyze. But some students may have a slight confusion between the levels of the factor and treatments. It will become clear if you also look at a 2-factor experiment. The treatments are properly defined this way. For a single factor experiment, the levels of the factor are called treatments. But for multi-factor experiments, that means 2-factor, 3-factor, or more than that experiments, the combinations of the levels of the factors are called treatments. Okay? So how many treatments we will have? the number of treatments will be equal to the product of number of levels of each factor. Okay? So if you have two factors, the first factor may have 4 levels, the second factor may have 3 levels, the total number of treatments will be 4 times 3, 12. We'll do an example and it will become clear. In a two-factor experiment, we allow 2 factors to affect the response variable. All the other possible causes that might affect the response variable should be eliminated. Okay. Now here's an example. Amount of wrapping necessary for copper wires is being studied at 3 different temperatures, 50 degrees Celsius, 100 degrees Celsius, and 150 degrees Celsius, and 4 copper contents, 25%, 50%, 75%, and 100%. What's the response variable? So the response variable is the amount of wrapping. Factors. We have 2 factors, temperature and copper content. Levels of the factors. The first factor, temperature, has 3 levels, 50 degrees Celsius, 100 degrees Celsius, and 150 degrees Celsius. The second factor is the copper content that has 4 levels, 25%, 50%, 75%, and 100%. And the treatments. How many treatments I will have? I will have 3 times 4 because I have 3 levels in the first factor, 4 levels in the second factor. We said you multiply the levels of the factors in order to obtain the total number of treatments. So I will have 3 times 4, 12 treatments. And what are those treatments? One example for a treatment is 50 degrees Celsius and 25% cotton. So this is one example for a treatment. Another example for a treatment could be 100 degrees Celsius and 100% copper. Likewise, you can write down 12 possible treatment combinations. All right, so those are the experimental designs. And in this class, we will not analyze any of the two-factor situations in the future. We will only analyze single-factor experiments. I just mentioned the two-factor case just to clarify the difference between factor levels and treatments. Okay? All right, and if you go ahead and read point number 12, there are a few things that are important to keep in mind. All right, so that's it about chapters 8 and 9, collecting the data. Thanks.